Okay, hello everyone. Welcome back to my YouTube channel. Today we have again a numerical example about short circuit analysis. Okay, this is my playlist about power system analysis, and as you must be aware, we are working on short circuit analysis. Okay, and today we have a very interesting example. The numerical example today is working some problems about asymmetrical faults. Okay, asymmetrical faults. In this case, in this very specific example, as you can see here, we are working with asymmetrical faults, and the most important tool that we use for solving problems related with asymmetrical faults is symmetrical components. Okay. And let's see what we have here. We have here a very basic problem. A three-phase synchronous generator has one terminal open and the two others connected together to the ground, okay? And this condition create a double line to ground fault, okay? Yes, this is an asymmetrical fault, and in this case, we are working with a double line to ground fault, okay? And if the symmetrical components are here, positive sequence 600 amps, negative sequence 250, and finally zero sequence 350. Okay. Now what we want to do is the following. Okay. What we want to do is using symmetrical components. Okay, I told you this is the most important tool, symmetrical components. The famous paper in 1918 of Sharp-Fortescue, and we want to use this very important mathematical tool in order to calculate the current into the ground and the current in each phase of the generator. Okay. Now, what is the situation? Well, it's very simple. In this case, what we are doing is something extremely simple. We have a synchronous generator. Let's assume that the synchronous generator, the model is like this. Okay. We have here the three-phase representation. This is the neutral point. Okay, and we have here A, B, and C. Okay, and one of the terminals is open. And usually we say that that is A, and that is the reason that the current here should be equal to 0, okay? And then we say that the two other are connected together and then to ground, okay? They are connected together and then connected to ground, okay? We can assume that this is a star-connected generator, and here we can assume that the neutral is connected to ground, okay? Here we have a current B, we have a current C, okay? And what is interesting here is that we have the positive, negative, and sequence currents, okay? Now the question is, how much is those currents and how much is the current going here neutral to ground, okay? This is a very simple problem. All my students, they must be able to do this with the closed eyes, okay? Okay, now let's go for the solution, okay? What is the first thing that you need to know, okay? The first thing that you need to know is that there is something that we call symmetrical components, okay? And in this case, there is a relationship between symmetrical currents, yes, and asymmetrical currents, okay? Here, I believe you can see that I am using the subscript 012, and those are the symmetrical components. And I took the symmetrical components from here, okay? Zero component, 350, perfect. Positive component, 600 minus 19, yeah, perfect. And finally, negative sequence, 200 at plus 19, fine, okay? From my classes of symmetrical components, you must remember this equation. This is basically the transformation moving from symmetrical components to ABC, okay? And you must remember that this matrix the matrix A is basically this mathematical transformation over here, this 3 by 3 matrix, and the individual components inside. You can see here this letter A, this is the operator, and the operator is basically a phasor with magnitude 1 and is rotating the phase angle by 120 degrees, okay? What we will do now is just put the numbers inside this, okay? And the first one is quite simple to see, okay? We can put the number together here. We can apply just basic mathematical calculations, but I stop here in A because I would like to show you something that we already predicted, okay? If you must remember this circuit over here, I say to you, A, the current going for this line, A should be equal 0. And as you must be aware here, is the demonstration that the current on A is equal 0, okay? Now, I believe all of you can do the job at home, and you can do the calculation. You can do the calculation for the current in phase B, and then we will obtain the phase B, okay? The calculation is extremely simple. The calculation is extremely simple. We got the current using the rotation, okay? What we are doing is simply um, using here the transformation, okay? And we can obtain over there that the current is basically 950 amps, and I sub B is equal a phase angle of 144, okay? Then we can do the same situation for phase C, okay? We can do the same situation for phase C, okay? Some of my students are wondering, and I know that they will ask me, okay, what is this? What is that? I don't know what is that. Okay, if the positive sequence, you must remember positive sequence is 600 at minus 19, okay? Yeah. And the negative sequence is equal to 250 angle 90 positive, okay? And I sub 0 is equal to 350, 19, okay? Are we clear? Yes, extremely simple. Something easy here, okay? Okay, now, what is the difference between this one and this one? Okay, there is no difference, because remember, from symmetrical components, there is a property. You can go to my classes, my slides, and you can check, and the symmetrical component, the zero sequence components, all of them are equal, okay? But now, what is the situation? What is the situation? What is the situation with positive sequence at a negative sequence, okay? Well, you must remember that, and let me use a piece of paper here to show you what is happening with the angles, okay? Okay. All of my students must remember this, okay? Zero sequence, all of them are the same, yes? But for the positive sequence, we have here I1, we have here IB1, and we have IC1, okay? If this one is 600 minus 19, this one will be, okay? You must remember here, from here to there, this must be minus, this should be minus 120, that equal to 240, yes? As a consequence, this should be 690 plus 240, that is 240 minus 19, that is 150. And this one should be 120 degree. This should be 600 angle, okay? And then minus 120 minus 19, that should be 30, okay? Something similar happened for the negative sequence, okay? For the negative sequence, what you need to care is, okay, this is I2, and I2 is 250, 90 degrees positive, okay? Okay, and then we have here the two other negative sequence, and this one is, in this case, this is IC2, and this is IB2. In this case, IB2 will be 250, and the angle should be 120, okay? That means 120 plus 19 is 210, and that is the reason that we have here this one, and we have here this one, okay? If you want to do the symmetrical component calculation in this way, there is no problem. If you like to do so, it's no problem. To be honest, I prefer the matrix way. And here you can see this is the phase B, and this one is the phase C, okay? Again, if you would like to check those calculations over here, please go to the slide, read some theory, okay? Anderson chapter number 9 have a very good discussion, okay? But if you wish, I highly suggest to go to my classes, to my slides, and check, okay? Okay, and this is the current for B, this is the current for C, and now what we need to do is calculate the current that is going by the neutral point, okay? To calculate the current that is going for the neutral point, what we need to do is, well, the neutral point, you must remember, we have here A, we have here B, we have here C, yeah? And this is a line to ground, okay? And here we have the current C, we have the current B here, and here we have the neutral current. And using Kirchhoff current law, of my student must realize that this is B plus C, and that's all, okay? You can do the calculation over there, okay? Okay, sometimes my students, they are very obsessed with the numerical results, okay? And because I don't have any support creating those documents, sometimes I can make typos, okay? If you look this presentation and you find a numerical typo, please let me know. I will try to solve it, okay? Okay, many of my students, they are completely interested on numerical solutions and check all the decimal places, okay? I am too old for that, and I don't do that by hand, okay? As you must be aware, I create a GitHub repository for my students, okay? If you have the opportunity, you can go to my GitHub repository, and over there, and you can find you can download the files. Okay, you can download the files related to these fault analysis classes. Okay. What I will do here is something very basic. If you come here, as you can see, this is my GitHub repository, okay? Some of my students, they are not familiar with the GitHub repository, but here there is a folder, and you can go for the repository related with faults, okay? And here you can find the MATLAB live script for the asymmetrical faults, for the symmetrical faults, and for the symmetrical components, okay? And what I will do now now is, okay, let me open the one that is related with this specific class. And I already downloaded, and it's open here for my students, okay? If you are here with me, you can see that this is the MATLAB live script. And you can see over here, three-phase synchronous machine has one terminal and all the explanation. As you can see over here, this is the data, input data, positive sequence 600 amps, negative sequence 250, zero sequence 350, okay? Also, please try to be specific and provide credits, original credits. Okay, this is the GitHub repository. This is the ResearchGate location, and going to business. Okay, you can see here I am defining using MATLAB code and using complex numbers inside MATLAB, the positive and negative sequence currents. Then I define the symmetrical components vector. Then I define what is the what's supposed to be the operator A. Okay, you must remember that it's 120 degree. This is the matrix A, and then it's something very simple. Okay, to calculate ABC, you need to multiply the symmetrical components vector by the matrix A. You can do that. Okay, and if you run here the script, you can see here the results, okay? Here you can demonstrate that the current in phase A is 0. Here you can compare the numerical results. Remember, my students love checking results and see if the professor make any mistake. And I don't know if I make a mistake. Let's see if there is a mistake here. And for the phase B, let's go and see. Phase B is 904. Phase B is 904, 144 degree. That is perfectly fine. That is the proper solution. Then let's go for the current C. Okay, current C is 904.157 amps, and the angle, the phase angle is 39. Yes, and finally, what we want to see is the neutral current. And the neutral current, I believe we already calculated, is 1050 amps. And let's see here at the at my presentation. Yes, that is the neutral current. Okay. The conclusion here, I believe, is easy for all of you to see that in this case, numerical results in my example and also here in the MATLAB script, all of them match. Okay. Again, this is just an advertising. I highly suggest that you be familiar with the GitHub. And if you go to the proper place, you can download the script. And of course, you can get the full numerical solution step by step with explanation, okay? That is the idea that I spent a few hours here at the very beginning of the year, January 2020. And you can see here the proper explanation, and on the right hand side you can see the numerical solution. Okay, if one of my students want to have more numerical decimal places, what you need to do is modify the MATLAB code. I believe all the students are able to do so, and from there you can get as many digital places as you wish. Okay. Well, thank you very much for watching this video. I hope that you find my explanation useful. And also, again, I highly suggest that you go to my GitHub repository at internet. Let me show again. You can go here to my repository, and you can find several of them, but for this very specific example, you can find over there that is a fault analysis, okay? Well, thank you very much for watching my video. See you in the next one. Thank you.